Earth, a unique planet, restless and dynamic.
It rises from the Earth like a giant fist, stretching out to strike the sky. A colossal, 900-foot shaft of rugged rock, one whose very name conjures notions of both awe and dread. Devil's Tower.
Devil's Tower is remarkable because you can drive across these sedimentary plains, see nothing but flat ground for miles and miles. And then this tall, dark tower emerges as you drive towards it. There is nothing like it in the surrounding area. The rock has a grayish, even a greenish gray color. And so as you approach Devil's Tower, it's a distinct, stark contrast to the sort of tans and browns of the surrounding sedimentary rocks.
Since then, many have asked, what could have caused this massive tower to form?
There are many theories about it, but there's no agreement on what it was that produced this miracle of nature.
It is made of volcanic type materials, but there's no other volcanic activity around it. So what caused this thing? We don't know the answer to that question. It's a really interesting conundrum.
Is Devil's Tower really a miracle of nature? Something that simply cannot be explained by natural and scientific laws?
As much as we like to walk around with the confidence that we know this planet and we understand the planet we live on, there seems to be nothing but mystery on this planet.
Most of the landscape surrounding Devil's Tower is composed of sedimentary rocks. These are rocks which are formed from broken or dissolved fragments of other rocks, and are usually deposited by water or wind. The oldest rocks visible in Devil's Tower National Monument were laid down in a shallow sea during the Triassic time, 225 to 195 million years ago. This dark red sandstone has a hardness of 6 to 7, and maroon siltstone has a hardness of 6 to 7, interbedded with shale. Shale has a hardness of 3 to 4. It can be seen along the Belle Fourche River. Oxidation of iron minerals causes the redness of the rocks. This rock layer is known as the Spearfish Formation. Above the Spearfish Formation is a thin band of white gypsum. Gypsum has a hardness of 2. It's called the Gypsum Spring Formation. This layer of gypsum was deposited during the Jurassic time, 195 to 136 million years ago. Climates changed and changed again. Gray-green shales, deposited in low-oxygen environments such as marshes, were interbedded with fine-grained sandstones, limestones. Limestone has a hardness of 3 layers and sometimes thin beds of red mudstone. Mudstone has a hardness of 2. This composition, called the Stockade Beaver Member, is part of the Sundance Formation. The Hulett Sandstone Member, also part of the Sundance Formation, is composed of yellow fine-grained sandstone, resistant to weathering. Yes, this particular fine-grained sandstone is very weather-resistant. It forms the nearly vertical cliffs which encircle the tower itself. Landforms were eroded. New sediments were deposited. About 65 million years ago, during the Tertiary time, pressures within the Earth climaxed, uplifting the Rocky Mountains and the Black Hills. Molten magma welled up toward the surface of the Earth. intruding into already existing sedimentary rock layers. We now are able to see the magma intrusion because 1 to 2 miles of these sedimentary stones, listed above, were eventually eroded away through the wind and rain, freezing and thawing over the last 5 to 10 million years. Erosion has dramatically changed the area around Devil's Tower. When the tower formed around 50 million years ago, it was 1 to 2 miles below the Earth's surface. Somewhere between 5 and 10 million years ago, erosive forces began to expose the tower. These forces, particularly that of water, carried away the sedimentary rocks above and around the tower. The harder igneous rock of the tower is more resistant to erosion, and the grey columns of Devil's Tower began to stand out above the surrounding landscape. As rain and snow continue to erode the sedimentary rocks surrounding the tower's base, and the Belle Fourche River carries away the debris, more of Devil's Tower will be exposed. At the same time, the tower itself is slowly being eroded. The evidence of this process is seen in the large boulder field of broken columns at the base of the tower, as well as many other rocks on the hillsides below the formation. Although small rocks fall from the tower with regularity, no one has witnessed a significant column fall in recorded history. The Belle Fourche means beautiful fork in the French language. The river was also known as the North Fork of the Cheyenne by many early explorers. The Belle Fourche River has its headwaters to the southwest of Devil's Tower, and is an important part of the ecosystems along the north edge of the Black Hills. It also had a starring role in the formation of the tower itself. The Belle Fourche River empties into the Missouri River, which in turn empties into the Mississippi River. The delta of the Mississippi River may be the largest delta in the world. It still is far too small compared to the amount of sediment it had to have dumped from the Great Plains. It is speculated that some 2 miles high worth of eroded sedimentary rock from the Great Plains had to have been deposited at the delta, yet the delta does not have near enough material to account for this amount of erosion. If the delta was sinking into the Gulf of Mexico, the sediment from the eroded Great Plains would be found at the bottom of the Gulf of Mexico. Huge amounts of oil exploration and drilling has taken place in the Gulf of Mexico. Therefore, we have the samples from throughout the entire floor of the Gulf. The material found on the floor of the Gulf of Mexico does not match what is speculated to have been eroded away from the Great Plains. Where did the eroded sediment go?
Mount Everest is a mountain located in the Himalayas, specifically in the Mahalangir Himal subrange, which lies on the border between Nepal and Tibet, as one of the natural wonders of the world.
Rock samples from Everest. It's a dangerous mission, and only a few people are willing to undertake it. Kenton Kool is one of the world's best high-altitude climbers, and he will embark on this geological mission to the summit of Everest. His instructions from geologists are to collect rock samples from 3 places. 1 from the summit, and 2 from lower down. Kenton's first sample is a gray limestone. It's soft and easy to break off. This is a sample of the highest rock in the world. 1 down, 2 to go. Kenton descends further to collect the next sample. Just below the summit, the rock changes. Climbers call it the yellow band due to its distinctive color. The rock is dramatically different from the summit. Much harder and yellow in color. This is a layer of marble.
All right, there we go. This is off the yellow band.
Kenton needs to take his final sample from this area of distinctive white rock. Granite.
Yeah, we've got quite a nice sample of the granite there.
Here they will be analyzed by the world's leading authority on Everest, Mike Searle.
So Mike, this is your summit rock. Now, that is from the top of the world.
Well, this sample, Kenton, is probably one of the most important samples of the whole expedition, so it's literally worth its weight in gold geologically. This came from the summit of Everest right there. The next rock down that you collected was from the Yellow Band. And even further down is another rock, a granite.
Almost a complete picture of Everest.
That's right, yes.
Fantastic.
Yeah.
These three rocks are the major components which make up Everest. The summit rock is cut into a thin section. So thin, light can pass through it.
Okay, let's have a look at this slide of a limestone that's from the summit of Everest.
The highest rock sample in the world reveals its secret.
Oh, that was interesting. What's that?
We've got a section here through a crinoid stem. A crinoid is a sea lily.
From fossil records, the section can be dated. It is over 400 million years old. The sea lily is evidence that the summit rock of Everest was formed in an ancient marine environment.
So from seeing this evidence, we can categorically say that this rock would have started life at the bottom of the sea floor. And then I've collected it from the very, very top of the world, from the summit of Everest itself. That's just amazing.
But a mystery is revealed. How had rock with marine fossils in it ended up on the top of Everest?
The rock I've got in my hand at the moment may look a bit boring and insignificant. It's just a pebble taken from the river, but it's actually a key clue as to the formation of the Himalayas and the evolution of the rocks. It's almost by magic, but when you smash a rock like this open, what it reveals inside is an absolutely beautiful fossil. And this fossil is what we call an ammonite.
This ancient creature is part of the squid family. It's proof of a complex ecosystem found in a deep ocean. Geologists piecing together the story of how Everest was made have shown that 400 million years ago, a wide ocean existed where the Himalayas now stand. Like a giant train wreck, India collided with Asia. The land and ocean floor that lay between literally folded up under the enormous pressure. Rock was not only pushed upwards by the collision, but also down towards the Earth's molten core. But the Himalayas were set to become part of a geological battle between catastrophic forces and powers which would challenge the very height of Everest. 400 million years ago, the Himalayas started out life at the bottom of an immense ocean. 50 million years ago, they were thrust into the skies as India smashed into the Asian landmass. Since that time, tectonic forces have created the tallest mountain in the world. Earthquakes. Each year, 264 cubic miles of fresh water, enough to fill Hoover Dam's Lake Mead 30 times over, pours down the slopes of the mountains. This water feeds some of the largest rivers in the world: the Ganges, the Indus, the Irrawaddy, and the Yangtze. But all this water is having a dramatic effect on the mountains. Fast-flowing rivers cut steep-sided valleys. High in the mountains, rain turns to snow, feeding glaciers which carve into the upper slopes. Rock and debris in the glacier have ground away at the rock underneath. All these forces are at work today, wearing away at the Himalayan peaks. Because the monsoon is so powerful, geologists suspect that Everest and the Himalayas are being worn away perhaps more quickly than any other mountain belt in the world. After years of research, Owen has discovered the maximum speed of erosion: 1.1 inches per year. That's 6 times faster than the Rocky Mountains and faster than anywhere else on the planet. That's 6 times faster than the Rocky Mountains and faster than anywhere else on the planet.
Let's recap, shall we? Exposing the tower. Erosion has dramatically changed the area around Devil's Tower. When the tower formed around 50 million years ago, it was 1 to 2 miles below the Earth's surface. Somewhere between 5 and 10 million years ago, erosive forces began to expose the tower. These forces, particularly that of water, carried away the sedimentary rocks above and around the tower. The harder igneous rock of the tower is more resistant to erosion, and the grey columns of Devil's Tower began to stand out above the surrounding landscape. As rain and snow continue to erode the sedimentary rock surrounding the tower's base, and the Belle Fourche River carries away the debris, more of Devil's Tower will be exposed. To summarize, 65 million years ago Devil's Tower was exposed from under 2 miles thick of overburden, sedimentary rock, that is, in a mere 5 to 10 million years. While at the same time, 65 million years ago Mount Everest started a journey towards the sky. The Himalaya mountains, including Mount Everest, experience the highest erosion level on the planet, 6 times more erosion than the Rocky Mountains, which are just to the west but much higher up in elevation than Devil's Tower. Above Devil's Tower in the overburden was limestone, yet on Mount Everest, the peak, which is limestone and mudstone, somehow has survived 65 million years. In the most erosive environment on Earth, this seems to be overlooked. The peak of Everest was for thousands of years at sea level, where the waves continually crashed into the rising mud, but somehow was unable to wash away the soft limestone and mudstone. There is one explanation that would remove 2 miles of overburden from around Devil's Tower, and at the same time raise up Mount Everest, preserving its soft, mud and limestone peak. What I am talking about is Noah's flood, and the subsequent end of the flood, where God said he would raise up the mountains, so that water would never again cover them. Psalms 104, verses 6 through 9. Thou coveredst it with the deep as with a garment, the waters stood above the mountains. At thy rebuke they fled, at the voice of thy thunder they hasted away. They go up by the mountains, they go down by the valleys unto the place which thou hast founded for them. Thou hast set a bound that they may not pass over, that they turn not again to cover the earth.